This is lecture number 5, and we're talking today about interfacing. In the background video, we saw a number of different kinds of circuits, different circuit ideas, concepts. In this lecture today, we're going to talk about actual circuits that would be used to connect device A to the Arduino, for example. So because there are so many different kinds of devices that could be hooked up, we have a number of things to cover. We're not going to cover all possible things, but we're going to cover the most important things. And so we'll look at this in detail. So let's begin this discussion on interfacing circuits. So here's an example of a couple of ways that we could have our system hooked up to some other device. So for example, over here we have, we have two different circuits. So in this case, we actually have an IC circuit that we can hook up. And so we have these signals that can be connected through a chip like this to connect to something else. So that's one example. Another example over here, even though it says computer, this could be our microcontroller. And we have it hooked up to stuff going over here. So we have audio out, ground, mic, and so the computer can hook up to a radio this way, and so forth. And so that way you can communicate things through a radio using a computer. So different ways to hook up things. So in talking about interfacing circuits, we have the basic circuits, and op-amp circuits. So we looked at all of these. These are all covered in the video on circuit basics, the basics of circuits. So today we're going to talk specifically about digital interfacing, analog interfacing, and power interfacing. So that's what we're looking at today. Actually, I think we're going to do analog first. So in terms of interfacing circuits, again, the basic idea is that we have two things we need to connect. And often their characteristics are not compatible, and so a circuit needs to be inserted in between the two to get the two to function or cooperate or work together, or however you want to say it. So to begin with, in order to understand how to interface things with the Arduino, we first need to understand what the Arduino is capable of, its basic characteristics. We have a number of different kind of characteristics we need to look at, and these characteristics are critical to understand so that we don't damage, so that we use the full capability and yet we don't damage the Arduino or the other circuit we're working with. So first we look at the Arduino voltage characteristics. We're going to look then at Arduino current characteristics and then some resistive characteristics. So operating voltage is 5 volts. That's what it operates on. It's a TTL level. Okay, so this is the Arduino Uno. If you go to another Arduino, like the Arduino Due, you'll find that works with 3.3 volts. So a little bit different, but anyway. Recommended input voltage. So the Arduino Uno has a barrel jack that you can hook into your power supply, and it'll accept anything from 7 to 12 volts. So for example, you can hook up a 9-volt battery to it, and that works just fine. The extreme input voltage. So this is the recommended input voltage. You could actually input a voltage in this range if you needed to. Again, the recommended is recommended. So but it's important to understand what the extremes are. Okay. So in case you happen to have something that's 12.5 volts, is that still acceptable? Well, according to this, it's certainly acceptable. Okay. The maximum voltage applied to any input-output pin, that's either digital or analog, is 5.5 volts. If you connect a voltage up to any pin that's greater than 5.5 volts, you can expect your Arduino will fry. Okay, so it's critical to understand this. So we definitely don't want to do that. Maximum voltage applied to the 5-volt pin. So it turns out that on the Arduino, there's a 5-volt pin on there, and sometimes people want to connect things up to that point. In general, another voltage supply up to that point. In general, that's just not a good idea. But so that in general, so certainly if you put anything above 6 volts, you're going to have problems. Similarly, there's the 3V3, which is basically 3.3 volt pin. If you hook up anything greater than 3.6 volts, you're going to have problems. And it turns out that you can apply voltage to the reset pin, and if you apply anything larger than 13 volts, I'm not sure why that's the case, but so it is, then you will have trouble. So these are the basic voltage characteristics. So maximums, you don't want to exceed those maximums. Arduino current characteristics. So the amount of current on any I/O pin, the maximum is 40 milliamps. So you don't want to put any more than 40 milliamps into the Arduino, and you do not want to try to get any more than 40 milliamps out of the Arduino. So for example, if you have, let's say, digital pin 3 and you set it high, so that then it's 5 volts. If you now short that to ground, then you have basically, you've attached a 0 resistance across from 0 to ground, which is basically going to allow potentially infinite amount of current. Well, obviously it's not going to be an infinite, but it's going to be enough to fry that pin. So obviously that's not a good plan. If you've put something high, it's going to have 5 volts on it, and so that we have that situation. So it's something to be careful about. Maximum current sourced from any I/O pin. So in general, if you want to drive something, for example, with the voltage high, 5 volts. So this is the source. Then notice that the source, so if you actually want to put out something, that's the largest it'll put out. So what this is saying is, if I connect something, the thing that you connect may want to draw a certain amount of current. For example, a short would want to draw a lot of current. But if you actually want to put out, that's the maximum you can actually put out. Okay, so it's kind of interesting when you think about current, how current arises in circuits. Again, Ohm's law still applies, but it's not always obvious to see what the voltage source is, what the resistance is, and so forth. So the critical thing here is that you can actually have more current allowable than you can actually put out. And in particular, again, this really occurs when you have a high, for example, a digital pin that you've set high. That's as much as you can expect to get out. Okay, if you have that digital pin and you ground it, it's set to low, so it's ground. It can actually take in 40 milliamps from whatever its source is. So basically, what this is saying is that you can sink more current than you can source. So that's why it's very common, for example, when you want to turn on an LED, to have a pull-up resistor from the LED, because when you set the pin low, then it acts like a ground and it can source plenty of current. Okay, so that's important. So the maximum current you can get from the supply voltage, if you draw more than 200 milliamps, that sounds like a lot, especially when we're talking about numbers like this. If you try to draw more than 200 milliamps from your supply voltage, you will fry your Arduino. Okay, not a good plan. Maximum current from each ground. Okay, so 200 milliamps. So so notice that there are 2 ground pins, and so because of the fact that you have 2 ground pins altogether, you can actually get 400 milliamps if you take both into account. Recommended steady state current is 1/2 of max. So even though, yes, you could conceivably get 40 milliamps, you don't want to do that. So this is maximum, this is recommended. Okay, similarly with the current sourced. Okay, so these are the current characteristics. Let's move on to the resistance characteristics. So inside the Arduino are internal pull-up resistors, and they're essentially 20k ohms, but not precisely 20k ohms. They can actually go up to as much as 50k ohms. But anyway, that's what they're estimated to be. They're estimated to be 20k ohms. Anyway, it's sufficient so that it's large enough so that if the pull-up resistor is connected, that you're not likely to allow a lot of current out of that pin. Steady state load resistance. Okay, so if you hook up a load to the Arduino in steady state, to keep things working properly, you probably want the resistance between 470 ohms and 10K ohms. When you set the Arduino pin up to be an input pin, when it's an input pin, it is switched into a mode that is called a high impedance mode, that is high resistance, and in that case it actually has a resistance of 100 mega ohms, so that's really large. So remember, for circuits, you want a high input impedance, low output impedance. So here we see we have a very high input impedance, or high state input state resistance, 100 mega ohms. So that's really good. So if you, for example, on an analog input, if you hook an analog circuit up to this, then this will not do much loading. So that's a really good characteristic that they have built into the Arduino. Okay, now we're going to move on to talk about analog interfacing. Again, the concept of interfacing is that we may have some device like a sensor which runs on maybe plus or minus 10 volts. The Arduino runs on 5 volts. Okay, and so we need some kind of a circuit that will connect this kind of voltage up to our Arduino. So here's, for example, an analog signal that goes into analog channel 1 and ground. Okay, and so our interface takes these signals over here, and it may have additional signals. For example, it may have, like a power connection up to it. So the idea is we want to, what kind of a circuit would we put in here to make all of this work compatibly, so that we don't have to worry about frying our Arduino, and so that we use the full range of the capability. So if you have a analog to digital converter, which our Arduino does, those are the analog inputs, and it has a range of 0 to 5 volts like this does, and that range corresponds to a 10-bit number. So these are 10-bit analog to digital converters. Then if we only have a voltage here that is at most 2.5 volts, then what that's doing is that's only using half of the range of the analog to digital converter. And so in a sense, it's like only using 9 bits of the analog to digital converter instead of the full 10 bits. And so if it's possible, it's best to set up your system so that you get maximum. Now, obviously, you want maximum, but you don't want to go over it, because remember, the input into an analog input channel can be at most 5 volts, so you don't want to go above 5 volts. So that's important to keep in mind as we look at this interfacing. So first thing we're going to talk about is something called an analog signal conditioner, otherwise known as a shifter and scaler. Shifting and scaling is what this circuit does. So we have some signal coming in. This is the signal that comes from our sensor. Okay, and in order to get it into the analog to digital converter on the Arduino, we need to scale it down, and we may need to shift it. So again, if you have a voltage that could be anything between 10, plus or minus 10 volts, well, first of all, 10 volts is outside of 5 volts, so definitely you have to shrink it down. Okay, that's the scaling. Then, since we have it from minus 10 to 10 volts, if you, let's say, shrink it in half, that goes from minus 5 to 5 volts. But the Arduino doesn't do negative voltages, and I should have put that on there. The Arduino doesn't do negative voltages. Okay, so you can't go minus 5 to 5 because the Arduino won't handle that. So you have to shift that whole range up so that it still fits within 5 volts, from 0 to 5 volts. So we basically need to transform our input from plus or minus 10 volts, from anything in that range, to something in the range of 0 to 5. We need to transform it. And so basically what we would do is we would use a transformation that looks like this. So this is like a slope-intercept, okay? And so the intercept is what's called a DC offset, okay? So we need to that's the amount you need to shift upward, okay? So our sensor signal itself is in between two voltages, S0 and S1, okay? And so that's the range it comes in. And so, for example, if we're talking about it plus and minus 10 volts, S0 would be minus 10, S1 would be plus 10, okay? So, so if you think about what's happening, let's suppose we're looking at the situation of plus and minus 10 volts, okay? And we want to get that down to 0 to 5 volts. Well, first thing we need to do is we need to scale it down by how much? Well, we need to scale it down so that the total range is 5. So to start off with, plus and minus 10 volts has a total range of 20. So we basically need to scale it down by 1/4 so that we get it down in the range so that the total range is 5. Now, if you scale it down by 1/4, that basically gives you, so over here, if we set K to be 1/4, then that would make this signal, instead of being plus and minus 10, it would be plus and minus 2.5. Again, I still have minus 2.5. That's still not going to help us. So I would need to raise it up by 2.5 so that what was minus 2.5 becomes 0. And so that would be setting this to be 2.5. So in general, if we have a case like this, when we have S0 and S1 set to be of this form, then this is the formula that we use to get K. So notice the S1 minus S0 is the total range. So notice in our example, if we're using plus and minus 10 volts, then S1 is plus 10, S0 is minus 10, so the difference is 20. 5 divided by 20 is 1/4, and that's what we saw, right? So but this works even if we have some other range besides plus and minus 10. Then B, the offset, is given by this expression over here. So again, the total range, and that divides this number. Okay, so notice S0 is a negative number if you're looking at plus and minus 10 volts, and so a negative number and a negative gives you a positive number, and that shifts it up. Okay, so that's why the negative sign. So this is in a block diagram form the kind of thing we need to do. We need to scale, that is by applying a gain. We need to multiply that by our signal. Then we need to offset. Okay. Now when we saw the op-amp circuits, we saw that an op-amp circuit can do both. It can do a summing, right? We had a summing inverter. We also had a gain, which was the inverter, and so both of those together can be used to create a circuit that would work for us. So here is an example circuit that would work for us. So this first op-amp basically does the scaling, and then notice this is and notice it scales and it inverts. This sums and inverts. Okay, and notice over here I have an S2, which is not S1 or S0. So here the voltage in is S, whatever S is. S2 is some other voltage. So for example, suppose we have a situation where we have in our circuitry that we're working with, let's say we have a supply voltage that's plus and minus 9 volts. Okay, so S2 would be 9 volts, which isn't anything related to S1, S. Okay, and so if we now choose the resistors, so again that K is given by this expression, B is given by this expression, and in terms of the resistors, these are the relationships. So given this number, for example, if we were looking at plus and minus 10 volts, then K would be given by this expression, and we would choose our resistor values to make these two things equal. And similarly with the B, we would choose our resistor values to make these two things equal. And so obviously I have more unknowns than I have two unknowns, and I have five. I have 5 unknowns and 2 equations. That means since you have more unknowns than you have equations, that means you have some what are called degrees of freedom. And so, for example, I could choose R1, well, let's see. I could choose, for example, R4 to be equal to R5. Okay, and so basically these two guys would cancel. And so I could choose R1 and R2 to make this happen. Okay, then I can choose R3 to make this, and so forth. In other words, we can choose a resistor. So R1 and R2 to make this happen. Then I can, since again I have one equation and 2 unknowns, then I would choose, for example, R1, let's say to be 10 kiloohms, and let's say make these two guys to be 10 kiloohms. So all of these are like 10 kiloohms, and so then R2 is going to be this times 10 kiloohms, and so that's what we would choose as the value. Now, unfortunately, this is not perfect because, the reason it's not perfect is because even though this formula would tell you what to choose, for example, for R2, it doesn't mean that you can actually find a resistor with that value. Okay, so this may give you some weird number, and there's not a resistor for that value. And so there are a couple of ways to work around that. You can tweak things, but generally speaking, again, you want to make sure that whatever happens, that you're within the plus and minus, the 0 to 5 volt range out here. Okay, this voltage, if this is plus and minus 10 volts, this can never be greater than 5. Okay, you don't ever want it to be greater than 5. So that may mean making K a little bit smaller. So in other words, when we choose a resistor, we may have to choose K a little bit smaller in order to make this happen, and that may require an additional shifting on B. But anyway, that's the kind of thing that we need to do. We may need some change here. Okay, so that is the analog signal conditioner, the scaler and shifter circuit. Now our first analog circuit that we're going to talk about, an interfacing circuit, is the simplest one, which is a potentiometer. A potentiometer, or a pot, is basically a variable resistance. Okay, so it has 3 terminals, and basically what's called the wiper, and the wiper can be set anywhere from one side to the other side of that resistor. Okay, so it can go from anywhere from one side to the other side. So if I move the wiper all the way up, then at this point the resistance between this point and here is 0. If I move the wiper all the way down, then the resistance between here and here is the full resistance that the pot has. So in this particular case, we have a 5 kilo ohm resistor. So 5 kilo ohm resistor then is the total resistance, and they make potentiometers of different resistance values. Okay, but either way, the resistance from here to here is 0. The resistance from here to here is the full resistance value, and then I can get any resistance in between. Okay, now in terms of this, here we've hooked up the potentiometer to 0 and 5 volts and 0 volts. Okay, and so the 5 volts we get from the Arduino, and the ground we get from the Arduino, and then the wiper, basically, when the wiper is all the way up, we get 5 volts. When the wiper is all the way down, we get 0 volts. Okay, and because the analog input has very little loading, then the resistance that is seen from here to ground is very large inside the Arduino. And so if I were to set the wiper halfway between the top and the bottom, I should get 2.5 volts. Okay, there's no loading effect. If if I had lower input impedance, I might get some loading effect, but in this case I would get no loading effect. So what the potentiometer allows us to do is to get a variable, well, it's a variable resistance, which allows us to get a variable voltage. Okay, and so I can get anything between 0 and 5 volts. So that's a helpful thing to have. So that's a very simple analog input circuit. In terms of analog outputs, and our Arduino has analog inputs. Okay, so there's not much we need to do. We've seen the scaling and the shifting and the scaling circuit, and so we would need to use a circuit like that if we were going to bring in something that's another voltage. So we've already seen that. Now, we saw the potentiometer. Now, in terms of analog output, we have these different options. We have pulse width modulation. We have an R2R network, which is basically a digital to analog converter. There are what are called hack methods and digital to analog converter chips and shields. Okay, so these hack methods that I mentioned can be found at this this website, Review of Arduino DAC Solutions. Okay, so they mentioned a number of methods that can be used. You know, they have some validity. They're not all that great, but anyway, they are methods, and there will probably be more as time goes on. Okay, pulse width modulation. There are two types of pulse width modulation. There's what's called unipolar, and then there's bipolar. So in unipolar pulse width modulation, that's the kind the Arduino has. It's between 0 and positive 5 volts. So in other words, unipolar means it only has one non-zero voltage. Okay? Whereas bipolar has two non-zero voltages that it's concerned with, a plus and a minus. So these are the two common means of doing pulse width modulation, either unipolar or bipolar. Now unipolar is used if you only need to go in one direction. Okay, so if you have a motor and you're only concerned about the speed in this, let's say the clockwise direction, then and you don't need to worry about it turning around and going back the other direction, then you can use a unipolar pulse width modulation. The bipolar is used if you want to go in two directions. So in the unipolar pulse width modulation, we have 100% basically corresponds to full speed on that motor. Or if we're talking about lighting an LED, it's 100% light. Okay. If you do 50% pulse width modulation, 50% duty cycle would correspond to half speed for a motor, and 0% would correspond to a stop. Okay. So the unipolar is nice because the Arduino does it directly, but bipolar is also another good way of going. For a motor, if you have a motor that can go both directions, then 100% basically is full positive, 50% corresponds to a stop, and 0% corresponds to full negative. Okay, so if you think about what's going, 100% means I only have 12 volts coming out. I have 12 volts coming out. 0% means that it only stays down here at minus 12 volts. Okay, so in that case, we have full negative. So these are the two different types of pulse width modulation. Now again, the Arduino does the unipolar, so the bipolar is a little more complicated. So it's common to use DC motors, for example, going either direction. Now notice you can't use the bipolar pulse width modulation if you want to light an LED. An LED has to have the current flowing one direction. The current will not flow the other direction. So bipolar doesn't work with an LED. It would work with a light bulb, okay, with a regular like incandescent light bulb, but not with an LED. Okay, so it's common to use DC motors going either or both directions, and it's common to use DC motors in positioning. In positioning, DC motor requires a closed loop controller, it requires a position sensor, and it requires that the motor be able to turn either direction. So in this case, going either direction, you may have a speed where you want it to go positive direction speed or negative direction speed. Okay, so those are some aspects of pulse width modulation. We'll talk more about pulse width modulation when we talk about the H-bridge in power. The analog out, true analog output. Okay, so how can I get out of the Arduino a voltage between 0 and 5 volts, anything between 0 and 5 volts, or any of a number of things between 0 and 5 volts. So this is one way of doing it. It's called an R2R network. It's sometimes referred to as a flash converter. And in this case, we're doing it with 8 bits. So here are the bits. And again, these would be connected up to digital outputs on the Arduino. Okay. And so notice you have R resistors down here and 2R resistors. So if this is 10K, then this is 20K, and so forth. Okay, and so we have this resistive network, and then it goes into a op-amp. And notice the op-amp may have external power supplies, and so what this is saying is you need a power supply up to 12 volts, or at least 6.5 volts, and up to 12 volts. Okay, so it turns out that when you use this network, it's possible to get a voltage here that is larger than 5 volts. Okay, it's possible to get a voltage here that is larger than 5 volts. So that could be a problem if you only have a 5 volt supply. Okay, so in general, you may need a larger supply for your output, but that's kind of like expected that you might need another supply. It's just not that convenient. Okay, so if you have another supply or 2 supplies, you can use something like some kind of D to A and A to D shield. So this is an example, and actually you will use this shield in lab. Okay, these shields, a number of them exist, are either SPI or I2C based, I2C based converters. And what does that mean? That means instead of taking up 8 bits to do 8-bit conversion, it means that you have that you just use the 2 bits, for example, for the SPI communication, okay, or the I2C communication. Okay, so instead of taking up the full 8 bits, the bits are sent serially instead of in parallel. So the reason the other one was called a flash converter is because it takes all 8 bits at the same time and does the conversion, does it right away. As soon as those bits change, that conversion value is pretty much ready. Okay, whereas this, you take the value and it writes out the value serially. So if you want to do if you have a 10-bit conversion, it's got to send out 10 bits before this guy can do the conversion. Okay, and so the shields can either do single-sided or double-sided inputs or outputs. So what that means is that you could have from 0 to some voltage, like 0 to 12 volts be your output voltage, or you can do plus or minus 10 volts, plus or minus 12 volts, like that. That's a double-sided. So these kind of circuits will generally do the shifting and scaling. So this particular one is an digital to analog converter. Okay, power DAC it's called, and it will do the shifting and scaling so that whatever number of bits that you use. In this case, I think this is a 12-bit converter, so that those bits convert to plus or minus 12 volts. Okay, so that's what that does. The last thing I want to talk about in terms of analog circuits is a low-pass filter. A low-pass filter is often desired because of the fact there are a number of reasons for wanting a low-pass filter. So one thing is it can be used to eliminate noise from a circuit. For example, it's very common that noise in a circuit is high frequency. So if you find that you're somewhere you're picking up noise, electronic noise, or what is sometimes referred to as electromagnetic interference, then you need some way of eliminating some of that noise. And so a circuit like this can do that. So you have a voltage in, voltage out, and this, the voltage out here is set so that the magnitude of the voltage in will basically be the same as the magnitude of the voltage out. The difference is that now you will reject frequencies higher than this value, and you will pass frequencies that are less than this. So a lot of things move relatively slowly, and so this value is what can be used to determine some of these things. And this is the actual theory behind low-pass filters is certainly beyond the scope of this class. In fact, I don't think you even get into them until EE 312, so that's a little way off. But this basically, this kind of a circuit can be used to filter out some of the noise before it enters your system. So that can be a useful thing. And this is actually what's called an active filter. There are also passive filters, but they don't work nearly as well, or in more particular, they create loading effects that are not that desirable. So, okay, so that's the analog stuff. Let's move on to the digital interfacing. Okay, so first of all, we have TTL interfacing. And again, we may be in an environment that is very noisy. So the theoretical says that we have a digital signal, right, at TTL level. However, the real world is still basically analog, which means even though we think that's 5 volts, it may be fluctuating, okay? And it may fluctuate to the extent that it would fry our Arduino. In other words, you can get voltage spikes that would cause the Arduino to fry. Not a good situation, okay? And it just happens. You work in an environment, and again, 5.5 volts. That's the extra 0.5 volts above the TTL level. It's only 10% of the overall value, but you can get large noise spikes sometimes. For example, if you have a circuit and lightning strikes nearby, it can induce some very high voltages, easily enough to fry your system. Or static electricity can be enough that you'll get a voltage that's very, very high. So, okay. So if you know your signal is at TTL level, then you can just bring it in. Okay. So in other words, if you know it's never going to exceed that, then you're good. However, in other cases, so line spikes, lightning strikes, and so forth, you may need something called an opto-isolator. So here you apply a pulse, or your digital input is here. And basically, when it's high, it turns on an LED. Okay, and so this is all inside the package. So the LED is connected to what's called a photo receiver. Okay, and so that will pick up voltage, and the output voltage then will basically be the same as the pulse. But if this goes large, it'll still turn on the LED. If this goes too large, it'll turn on the LED, but this side of the circuit, which is where your Arduino is connected, is not physically connected. It's connected optically. Okay, it's connected optically. So the light here is what communicates this pulse or this digital signal to this output. Okay, so you don't need to know all the inner workings of that, but needless to say, an opto-isolator is very commonly used in automotive applications, a lot of industrial applications. Okay, so that's important. The next thing we have seen is the pull-up resistor. Pull-up resistor we're going to see all over the place. Basically, it connects something up to 5 volts. Okay, and that something makes this voltage down here basically 5 volts. Whenever this is 5 volts, then this will be 5 volts. Okay, and so basically that means I'm not getting any voltage drop across this device. Okay, and so when this goes 0, okay, when this goes 0, then this becomes 0, and then current flows. Okay, so it's very common to use pull-up resistors. We'll see them all over the place. Okay, very important in terms of, remember, the outside world is still analog, and so that's why we have to throw in resistors and stuff like that. Sometimes we'll throw in capacitors and other things because they're important. Now, so remember, a resistor, it has a constant resistance. A capacitor actually does not have a constant resistance. It depends on what's applied across it as to what resistance it has. But you can think of a capacitor as being a DC open circuit and an AC short circuit. That's one way of thinking about it. And we're going to talk more about, we're going to see some examples of circuits that require capacitors, like this one. Okay, this one requires a capacitor in here. So basically the R and the C provide a kind of low-pass filter here. And we're going to talk about now here the switch debouncing. So we've talked a little bit about the fact that a switch, when you switch it on, so you may switch from one place to another. When it switches, it may bounce. It may, okay, and it may bounce several times before it finally settles. Okay, well, in terms of a digital signal, that basically means that, you know, if this is the thing we're trying to, or rather, let's say this is the side of the circuit we're attached to, it's like we may be going 5 volts, then less than 5 volts, 5 volts, less than 5 volts, and so forth. Okay, and so as it bounces, this signal goes between 5 volts and something else. And so if we're looking at a high to low transition, you might get several transitions occurring in a very short amount of time, where you really only wanted one transition. Okay, that's the notion of bouncing, and it's a very significant problem with mechanical switches when you hook up a mechanical switch. So if you have an optical switch, it's not the same thing. You don't get the bouncing, but with a mechanical switch, you can expect to have bouncing. Okay, so here are a couple of debounce circuits that can be used. This first one involves some unusual. So here's our switch, and basically this is the kind of, this could be, here I have a switch that looks like this. When this guy touches, then it makes contact. The other kind of switch we've seen is like a push button switch, where it's not connecting either side until you push the button, and then it connects both sides together. Okay, so a number of different kinds of switches. I probably should have talked about switches. Different kinds of switches. You have single pole, double throw, and so forth. All different kinds of switches too. I probably should talk about them. But anyway, we'll move on. Okay, so here I have a resistor, a diode, another resistor, and I have here an inverter that has what's called a Schmitt trigger. Okay, Schmitt trigger is a digital device that can help clean up circuits, the output of circuits. It does something a little interesting, but anyway, this is one example of a circuit. And so basically what happens is, since that thing is bouncing, oftentimes it doesn't bounce up and all the way down. It just bounces up near one side. So that means I get 5 volts and then something that's not 5 volts. 5 volts and then something that's not 5 volts. And so, or sometimes it can actually bounce, but it doesn't usually do that much, that kind of bouncing, but it can, so in some cases. And so, what this does here is it provides a low-pass filter kind of situation. And so basically so this switch is touching. Touch, 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 touch. Okay, touch, 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 touch. And then, but this signal here has been low-pass filtered. So the basic idea is these things that happen, these contacts happen very quickly. Okay, and so basically this is intended, and depending on the value of R and C, you can make this respond slowly to those taps. Okay, so that's what this circuit is intended to do. So that's one way of doing it. This is another way, and this uses logic gates directly. These are NAND gates. Okay, and so notice that this is a different kind of switch. Okay, this is what's called a single pole. So this is called a single pole, single throw switch. So this is the pole. This is the thing that it's attached to. And it touches one contact over here. It can only touch one contact. So single pole, single throw. This is a single pole, double throw. In other words, this switch contact can be in either of two positions. Okay, so this is either on this contactor or it's not on that contactor. In this case, it can be either on this contactor or on that contactor. So it's a different kind of switch. And to handle this kind of switch, then we use this kind of a circuit. Okay, so notice both of these. I actually have two pull-up resistors. So even though this is down here, this is actually a pull-up resistor. Okay, and then you have this logic, this NAND logic. It's kind of tricky to follow. It's a little tricky to follow. Yeah, so each of these have their advantages and disadvantages. Some of these they work well, some not so well. And a lot of it depends on how rough that bouncing is. If the bouncing is simple, then most of these will work well. If the bouncing is really complicated, it may be difficult. So these are hardware switch debouncers. We can also have software switch debounces, which you have already seen somewhat in some of the examples, homework, and so forth. Okay, suppose we want to then connect up digital to digital. Okay, so CMOS is one form of digital technology. TTL is another form of digital technology. Okay, so TTL basically has these acceptable ranges. Okay, so this is TTL ranges. So in TTL, actually this is TTL to TTL. So this signal is TTL input level, these TTL output levels. Okay, so just to kind of see what's going on with that. Now, in TTL, anything between 0 and 0.8 volts is taken as a logic 0. Anything between 2 volts and 5 volts is taken as a logic 1. Okay, so for a TTL signal, that's the definition. Those are the defining properties. Okay, anything less than 0.8 volts is still considered a logic 0. Anything above 2 volts. So remember, we're talking about, even though we're talking about digital circuits, the world is still analog. Well, the fact that this kind of situation happens means that the designers of TTL circuitry recognize the analog nature of circuits. So in here, we have a larger range for high than we do for low. So a TTL gate will accept these and make these definitions. If I have anything between 0.8 volts and 2 volts, the TTL does not know what to do with it. It will arbitrarily assign a value, either positive or, a 1 or a 0. It will arbitrarily assign a value. As far as output is concerned, in TTL, the TTL circuits are designed to put out as a high something between 2.7 and 5 volts. So notice that a TTL level is not guaranteed to put out a 5 volts as a 1. Not guaranteed. That's kind of surprising, isn't it? Not guaranteed to put out 5 volts. It's going to put out something between 2.7 and 5 volts. That's considered acceptable according to the TTL standards. Okay. As far as output is concerned, a low is going to be between 0.5 volts and 0 volts. So usually we think of a low as being grounded. Well, as you can see, it's not necessarily grounded. Okay, not necessarily grounded. It could be 0.5 volts. Okay, so but it's this region. So anyway, these are the definitions for TTL. These are the definitions for CMOS, for 5 volt CMOS. Okay, so the input levels are between 3.5 volts and 5 volts, and that for high, and for low it's 0 to 1.5 volts. So it will accept these. CMOS will accept these. Okay, so notice this will accept 1.5 volts as a logic low, whereas this will not. Okay, this will not. So 1.5 volts here is going to mess you up over here. I'm sorry, 1.5 volt here that will be accepted by CMOS is not acceptable by TTL. Okay, and this 2 volts down here that's acceptable by TTL is not acceptable by CMOS. Okay, it's not acceptable as a high by CMOS. So there are some conflicts. Similarly, for CMOS, the metal oxide semiconductors are very good at switching. They're very effective at switching, and so the output levels that you'll get out of CMOS will be 4.9. That's 5% error, 5% off. 4.95 volts to 5 volts. Very, very close to 5 volts. CMOS is very powerful that way. And the output low will be 0.05 to 0 volts. So this is like, it's at 1/10 of that range. Okay, so CMOS, it's very good at switching. And so CMOS is very good at being able to clean up signals. It's going to give you either a 5 volts or 0. Very close to 5 volts or very close to 0. Okay, so now how do you convert between the two? Well, here are some circuits that can be used. So this is a circuit that can be used to convert. Oh, the other thing about CMOS is not necessarily 0 to 5 volt. Okay, CMOS could actually be other voltages, for example, 10 volts. Okay, so that's an issue that would need to be dealt with. So here's a circuit that would convert from TTL to CMOS. Okay, so here, notice in this case we have VDD instead of VCC. Okay, and so anyway, here's a conversion circuit. So notice it involves 2 inverters. One, it's a TTL level inverter. The other, it's a CMOS level inverter. And so that's if you have TTL in and a CMOS out. Here, this is TTL in and CMOS out at a higher level. Here's TTL and CMOS out at a higher level. So notice there's a number of different things that can be used. Notice that in between here, this one actually uses a buffer. Okay, so more complicated circuit. So these are some circuits that can be used to do the conversion from TTL to CMOS. And so here's a CMOS to TTL. We have a circuit like this. Here's CMOS to TTL at a higher level. So this is a 5 volt CMOS. This is 10 volt CMOS to TTL level. So we have a number of different options that can be used in converting from CMOS to TTL and back. Another digital interfacing that's needed is TTL to RS-232. RS-232 is an old serial communication standard, but it's still used quite a lot. Typical voltage values for RS-232 are plus and minus 25 volts, but they could be plus and minus 15 volts, but they could be as high as 25 volts. And it's not uncommon to see plus and minus 9 volts. Okay, so this kind of circuit would connect from the Arduino up to the computer. So notice that the RS-232 communication standard is a bidirectional communication standard, and it allows you to connect and communicate both directions, or what's referred to as duplex communications. Okay, so that is, it can transmit and receive at the same time. So notice that we actually, in going to this, we actually rely, which in some ways seems kind of like cheating, but it's not cheating, it's just doing the job, right? Connecting up a special purpose integrated circuit to do this. And look at all these capacitors you have to hang on there to get it to work. So anyway, that's the conversion. There's also an interfacing that's needed for the I2C communication protocol, but we'll talk about that when we actually talk more specifically about the I2C communications. Now we're going to move on to power interfacing. Power interfacing. Okay, so the first thing is a digital power output. Okay, so what are we talking about? So the Arduino, we saw, can put out maximum on any pin, or can take in 40 milliamps. For many applications, that's simply not enough current. So, for example, a motor. Well, obviously, for example, if you wanted to hook up a 100-watt light bulb. Okay, that is if we wanted to use our Arduino to turn on a light bulb, like a 100-watt light bulb, or even higher watt, like stadium lights or something like that. Obviously, those lights are going to take much more current than the Arduino can put out. So what we need to do then is we need to have some way of being able to. So we know that a digital signal is like a switch, right? So what we need to do is connect up our digital input to some kind of a switch that can actually handle that kind of current. Okay, so a common way to do this is using something called a relay. A relay is basically a switch, okay, but it's an electrically controlled switch, okay, as opposed to a mechanical switch, okay. And so here is a way of hooking up a relay to an Arduino. So we have some pin that we're connecting, 0 and 5 volts. Here's a resistor. I think that should be like 10K ohm resistor. And then here is this is a transistor, or actually I think it's a Darlington resistor, but it's used as a switch. Okay, so here this pin is like a switch, which is connected to another switch, which is connected to yet another switch. So there are a number of levels of switching, each one able to handle more current. Okay, so basically this one is able to handle more current than the Arduino can handle, and then these contacts over here, this switch basically handles even more current. So how does a relay work? So a relay basically, as I mentioned, is an electrically controlled switch. And so what happens is when you apply power across the relay, so here's the relay, has these two power connections. Okay, so a relay basically has 4 connections, 2 for power, okay, and then 2 are the connections for the contacts. Okay, so when you connect power, basically what you're doing is you're applying a voltage. You're applying voltage across a coil, an electromagnetic coil, electromagnet, basically. Okay, it's an electromagnet, and so when you apply power, it turns the magnet on. And what the magnet does is it has these 2 contacts, and one of these is magnetic. Usually it's this one over here is magnetic, and so when the magnet turns on, this guy gets pulled over and touches the other guy. Okay, so you have these 2 contacts and a magnet, and when the magnet turns on, this guy gets pulled down and they touch. Okay, they contact. Okay, and when the magnet turns off, then it releases. Okay, and so these contacts can handle more current than these contacts, which can handle more current than this pin. Okay, so it's like stages that are used to allow us. And so with a relay, so here I have it hooked up, for example, to 24 volts. Let's say we want to control a motor with 24 volts. This can allow us, so instead of using 5 volts, we can hook up 24 volts. Or this could be like wall current, 120 volts. Okay, or whatever voltage is needed. Okay, so using the appropriate kind of relay, and there are relays that can handle different kinds of voltages and currents. Using the appropriate kind of relay, we can switch larger currents. And so, for example, it may require so much that we would use a relay to drive yet another relay in order to do what we need to do. Okay, so we saw how we used one switch to control this switch, which controls something else. We could use this switch to control even another switch to control something else, and so forth. Okay, so if you don't have it available with what you have, then you make you build up from there. Okay, so this is the basic digital output for power. Okay, so this can allow the control of large power, which can be very important. Pulse width modulation. Okay, pulse width modulation is great, and we've seen we can, for example, light an LED and change the intensity of a light with an LED. But LED requires very little current. What if we wanted to control a motor? Okay, so what if we wanted to control a motor? So the transistor then here can be used to switch high currents. So notice this is a little different transistor. This is a tip 120, and And so notice here, I don't have 5 volts, I have 12 volts. So it turns out, because this is not connected directly to the Arduino is not going to see that 12 volts. Okay, this 12 volts is used by the motor, and so this acts like a switch. So when this switch is grounded, basically I'm getting 12 volts going across the motor. Okay, and so this transistor can handle much more current than that other relay transistor that we saw, the BCX38B. Okay, so that's how this works. So this is a 12-volt motor, DC motor. Okay, and so the transistor again handles a higher current than the Arduino can handle. So the current that comes out of this, notice it's going through a 10K resistor and then to ground. So there's not much resistance that this pin is going to see from this circuit. It's going to see at least 10K of resistance. Okay, and so that's not a lot. Now notice there's also a diode in here. So even though this is just a switch, what's this diode? Well, it turns out that the motor, which if you remember anything about DC motors, DC motor has a winding in it that's wrapped around some metal, and when you wrap metal around, you basically get an electromagnet. But in addition to electromagnetism, you also get something called inductance. And so the inductance is what creates the magnetic field that the DC motor uses. And it turns out that when you turn off the power, that still has magnetic field that's kind of floating around in it, and that magnetic field can go back into the circuit and create what's called an inductive kick. Okay, and what can happen then is when you have that, when you turn this thing on and off, you're constantly putting energy into the magnetic field, and when you turn it off, the magnetic field collapses, and when it collapses, it creates a voltage. Okay, and so and in fact, the faster the switching, the larger the voltage. So that's that's kind of an interesting situation. And so if you try to apply, if this voltage becomes too large, it's going to fry your power supply. Okay, not a good plan. Okay, not a good plan. Don't fry your power supply. All right. So it turns out that just by adding a diode around here, that's sufficient to avert that. And so what happens is, instead of the extra current coming from the motor, instead of it heading off into the power supply, it kind of circulates through this diode. So that's called what's called a freewheeling diode, but it helps prevent that. So again, unipolar is used only when the motor speed control is going one direction. So if you're only concerned about one direction of the motor, then that's where you would use unipolar. We also talked about bipolar pulse width modulation, and so bipolar pulse width modulation is when you want to be able to go both directions. And so it's common to use something called an H-bridge. An H-bridge is the device that's used when we want to go both directions. So here's our motor, and it's within this. So here I have this arm and this arm, and then the H. The motor is in the middle. Okay. So notice this only requires one supply, and then we have these switches, 4 switches. Okay. So that is the conceptual idea of the H-bridge. And so depending on how we connect these switches, I can get this motor to do different things. So incidentally, that's the conceptual idea. Here's the practical implementation of that, and you can see it's a lot more complicated. We use these MOSFETs, or this is one way of doing it. There are actually many ways of doing it. This is just one way, and with a freewheeling Schottky diode, and we have pull-up resistors, and you may have a capacitor for EMI suppression, and so forth. So a lot of stuff is going on here that basically simulates this. So A prime and A, B prime and B, we're going to see those are important connections that can be made. Okay, so but this is a common implementation of the H-bridge using actual circuits. So instead of having just switches here, we're not going to actually use mechanical switches. We're going to use electrically controlled switches, which a MOSFET is a type of electrically controlled switch. So there are a number of different ones. Okay, so again, depending on where you put the switches, you can get different things happening. So first of all, when all the switches are opening, that's called a free running condition. The motor, so for example, when you want to shut the motor down and let it coast to a stop, you can do it this way, and basically there's no current flowing through the motor at all. Okay, so the motor runs and it shuts down eventually. In this configuration, when we close this switch and this switch, the current can flow through the motor this way. The voltage across the motor appears this way, and this will allow the motor to turn right, or which would be clockwise. Okay, so this is how. So this connection of switches would allow the turning right. If we close now these two switches, then the current can flow this direction, and notice now the voltage across this thing appears in the opposite order, and this would cause the motor to turn left or counterclockwise. So we have these two configurations that can allow us to turn right or to turn left or to run freely and to slow to a stop, or we can have something called resistive braking. So when I close these two switches, notice the current there. So let's say I was in this configuration with this switch closed, that switch closed, and these two open. Suppose I open now this one and close this one so that we're in this configuration. That may give us what's called resistive braking. Similarly, I could do the same kind of thing here. So basically, here, the motor itself has resistance in it. Okay, so it has an electromagnet, but because it has wire, and long wire that's coiled up to make an electromagnet in there, because it has that, it has resistance, and this resistance, when it's in this configuration, basically takes energy. In other words, when the motor's spinning, it has what's called kinetic energy, and when you hook in a resistor like this, the resistance in this loop then is enough to create to dissipate energy so that you can actually brake faster. So in this configuration, friction in the system will cause the motor to eventually stop. In this configuration, you not only have the friction, but you also have the resistance that also dissipates energy. So what's going to happen then is, in this case, this will stop, but it will take a longer time to stop, depending on the inertia of the system and the motor. In this case, when you stop, it actually provides kind of a braking action. So it's not exactly a brake, but it's noticeable. This configuration will stop much faster than this. So we have an H-bridge. An H-bridge has 4 switches. So each switch has an open and a closed position. So basically, there are 2 to the 4 combinations of things that can happen here. Okay, 2 to the 4. 2 to the 4 is what? 15, right? Or actually 16. 16 combinations. Okay, and so notice we only have 4 of them here that are actually used. Okay, 4 of them are actually used. In other words, we never use this configuration when all 4 of these are closed. Okay, we never use that. We could use it, but we just never do. Okay, we never use them when these guys are both closed at the same time, or these guys are both closed at the same time. We never do that, and because basically that's shorting your power supply. You don't want to do that. Okay, so there are a number of configurations we definitely don't want to have happen, and so the trick then with an H-bridge is synchronizing the switching of the motor. So this kind of situation is often used with pulse width modulation. Okay, pulse width modulation, you're switching between bipolar pulse width modulation is a switching between remember, the positive voltage and the negative voltage. Okay, it's switching between positive and negative. So basically, it's actually switching between these two situations, when these two guys are closed, and then when these two guys are closed. So there's definitely a lot of coordination that's going on in the H-bridge to make that happen. Okay, so but the H-bridge is a very important component in working with with motors. It can also be used for other devices. And again, this is just like a simplified version. It can also be used with other devices, but it's not commonly used with. The motors are the most common way that they're used. Okay, you can also have what's called a linear power amplifier. So the linear power amplifier is when you have a voltage, you want any voltage, say between -10 and 10 volts. Okay, so you would be working with a digital to analog converter. That analog signal, you may want to have a power version of that. So that digital to analog shield that I showed you can do the analog, but the amount of current that thing can handle is very little. So for example, if you wanted to drive something like a light or a motor or something with that higher power, you're going to need what's called a power amplifier. Okay, so a power operational amplifier is one example. So here are a couple of circuits that do power, or this is actually a chip that's basically a power op amp. So it's an op amp, but it can handle high power. Okay, so it's specifically designed to handle large currents, maybe 30 amps. I think this one can handle 30 amps. Okay, so that's a lot of amperage, okay, for an op amp. Here's another power amplifier. Okay, so notice often you'll see a lot of heat sinks when you work with power devices. So a heat sink, basically these devices can get hot. Okay, and so a heat sink is used to take that heat away. If devices get too hot, they can fry, right? So even though their voltage is in the right range, they can accumulate heat, and that accumulation of heat can cause the device to fry. And so it's very common to have the devices connected up to heat sinks that'll take away the extra heat. So it keeps the device cool. So that's very common. You'll see them in computers all the time. Microprocessors generate a lot of heat. So the microcontroller, because it only works at, say, 16 megahertz, that's not that fast. When you start getting up into the gigahertz range, you definitely want some kind of a power heat sink to remove the heat. So the sink basically is like a drain, takes the heat away. So the model of power amplifier that you use depends a lot on the frequency range for what your application is. So low frequency, audio frequencies, or radio frequencies, these are the general categories that they fall into. Low frequencies, for example, you can control a motor using a power op amp, and that's very common instead of an H bridge. But that's low frequency. In other words, in this case, you're not actually doing the H bridge. You're actually supplying a variable voltage. Okay, and so that can also work, and that can be used for control. And in fact, in closed loop controls, that's often desirable, is to use a power amplifier. So that's low frequencies, relatively low. So I mean, when we're talking about low frequencies below about 100 hertz are considered pretty low frequencies. But if you think of a motor changing direction 100 times a second, that's really fast for a motor. Okay, human reaction time is about 10 hertz. Okay, 10 hertz. So 100 hertz is like 10 times faster than a human can respond to something. Okay, so that's pretty fast. Okay, but even so 100 hertz is really low. So even 500 hertz is fairly low frequency. Okay, audio frequencies go up to 20 kilohertz, sometimes up, and depending on the circuit, you may even want 40 kilohertz, so 40,000 hertz. That's pretty large. Radio frequencies, we're talking about megahertz, maybe even gigahertz range. So each of these has a different range, and depending on the ranges, you have a different circuit that can handle those kinds of signals. Okay, so these are linear power amplifiers. So we've talked about analog circuitry, digital circuitry, and now power circuitry. And this then is a basic overview of the kinds of circuits we would use to interface with an Arduino to accomplish various things. So this is a very fast overview, covers a lot of ground. So I recommend that you look at this more than once in order to grasp all the different things that are going on. So, but this is the interfacing of circuits to the Arduino. Thanks for watching.